Hi everybody, this is Mr. Short. Today you can see we're going to be balancing chemical equations, and we'll learn about how that relates to the law of conservation of mass. A lot of times in 9th grade physical science, teachers might teach you how to balance chemical equations, but they might not relate it to the law of conservation of mass, so I want to make that connection real strong here. Alright, to start with, we have the guiding question, what am I trying to do, what am I trying to accomplish when I balance a chemical equation? So when we balance a chemical equation, what we're trying to do is to get the same number and type of elements on the left and the right hand side of the reaction. Okay, so when we balance, we try to get the same number and type of elements on the left and the right. The reason that we do this is because of the law of conservation of mass. This law says that mass or matter is neither created nor destroyed in chemical or physical changes. Rather, mass is conserved. The word conserve means that whatever number and type of elements you begin with, you have to end with the same. So this is the connection to balancing, which is up here. All right, how do we balance chemical equations? So chemical equations are balanced by picking coefficients. We've got a math term that we're going to emphasize here. So we choose coefficients, which are whole numbers that go in front of chemical formulas, in order to modify the number and type of each element in the chemical equation. And I'm going to teach you a simple strategy called making an accounting table, and we'll show that right down here. All right, when we make an accounting table, we take a look at the reactant side of the reaction arrow, so the left-hand side, and we just list the elements in order that we see them. So we see hydrogen and then oxygen. Whatever order I list them in right here, I'm going to list them in exactly the same order on the product right-hand side of the chemical reaction. Now I take account for the initial number and type that I have. I've got 2 hydrogens on the left. I also have 2 oxygens on the left. I have 2 hydrogens on the right, but I've only got 1 oxygen on the right. So because we made this accounting table, it lets us see, we can easily scan left and right across the reaction arrow. We don't have the same number and type of elements on the left and the right. Specifically, we're missing an oxygen, and the law of conservation of mass says that mass is conserved, so whatever we start out with, we have to end with the same quantity. So what we need to do is we need to pick whole number coefficients to go on these blank lines to balance out the chemical equation. Since I have fewer oxygen atoms on the right, I need to work on the right, and the whole number coefficient 2 will go right there. Now I like to draw these swirly distribution arrows as a reminder that this is 2 times 2 hydrogen atoms, which is 4 hydrogen atoms, and also 2 times 1 oxygen. That gives me 2 oxygens. Now notice that we picked this coefficient which balanced out oxygen at the expense of unbalancing hydrogen. That happens sometimes. You'll just go to the left-hand side of the reaction arrow right now and pick the whole number coefficient 2 right there to balance out hydrogens. And because we've been nice and neat and organized in our accounting table, our eye can easily scan left and right and see that we have the same number and type on the left and on the right. Now let's think about what this means conceptually. Having 2 diatomic hydrogens means this. Here is 1 diatomic hydrogen, and here is the second diatomic hydrogen. So 2 diatomic hydrogens gives us a total of 4 hydrogen atoms, but we have 2 completely separate molecules of diatomic hydrogen. Likewise, this is an understood coefficient 1. We have 1 diatomic oxygen molecule. Over here, we have a coefficient 2, meaning 2 water molecules, and you can see that we've got 2 water molecules right over here. Moving the paper down, I just want to emphasize one more thing. Remember, the way that we properly balance chemical equations is by picking coefficients, whole numbers that go on these lines out front. Here's what we do not do. We never change subscripts in order to balance a chemical equation, because if you change the subscript, you change the meaning of that chemical sentence. So here's what some students will want to do. They'll say, okay, I've got 2 hydrogens here, I've got 2 hydrogens here, 2 oxygens here, but only 1 oxygen right here. So they'll want to change that subscript. But it changes the meaning of this chemical equation. H2O2 is hydrogen peroxide. It's the stuff in the brown bottle that you use to treat cuts. Okay, so we've changed this from a synthesis reaction that creates water to a synthesis reaction that creates hydrogen peroxide, which we can't do. Okay, so again, all we can do is to balance with coefficients, never by changing subscripts. Okay, flipping over to the back side of the notes, we have the guiding question over here. It says, how do I balance equations in which polyatomic ions are unchanged? So if you take a look right over here, see how we've got the polyatomic ion sulfate. It's got the formula SO4 and it's unchanged on the left and the right-hand side of the reaction arrow. Okay. In contrast, we have hydroxide right here, but we do not have hydroxide on the product side because it's been converted into water. Okay, so just keep in mind, in this example, we've got sulfate, which is unchanged on the left and the right. Here's the best way to approach this. The best way to balance a chemical equation in which polyatomic ions are unchanged is to give the polyatomic ion its own line in the accounting table, and we're going to create that in this example below. So here's what I'm going to do. I'm going to have a potassium line, oxygen line, hydrogen line, and a sulfate line. Remember, sulfate has a -2 charge. So K, O, H, and a sulfate line. Okay, I'm going to take account for the initial number and type that I have. 1. I've got 1 oxygen right here. I've got 1 hydrogen plus 2 hydrogens right here. That's a total of 3 hydrogens. And then I've got 1 sulfate right here. A lot of students will tell me that this is 4 sulfates, but remember the formula for sulfate is SO4. I have 2 potassiums, 1 sulfate, 2 hydrogens, 1 oxygen. Okay, so I can see that the potassiums are out of balance, so I think that's a pretty good place to start. So I need to work on the left-hand side because I have fewer potassiums on the left, and I'm going to put the coefficient 2 right there. Now remember, this distributes, so it's going to change potassium, oxygen, and hydrogen on the reactant side. So I have 2 potassiums, I've got 2 oxygens, I have these 2 hydrogens plus these 2 hydrogens. That's a total of 4 hydrogens. On the product side, now I can see that I've got fewer oxygens and hydrogens here than I have over here. And notice that we've got 2 oxygens on the reactant side, but only 1 on the product side. So I need to go up here and I can spot that I need the coefficient 2, because that now gives me 4 hydrogens, 2 oxygens, and now my eye can easily scan left and right and spot from the accounting table that this is balanced. Moving down to the bottom of the page of notes, we have a guiding question about combustion reactions, so we need to talk about the pattern of combustion reactions real quickly. So remember, combustion reactions always have a hydrocarbon plus diatomic oxygen, and it always makes carbon dioxide, water, and releases energy. So this is a good example right here of a combustion reaction. So here's what we do when we balance combustion reactions. When we balance these, we always save oxygen for last. Really important statement right here. Okay, I'm going to really emphasize that. Save oxygen for last. I'm going to make my accounting table. Take account for the initial number and type that I have on the left and the right. And it really doesn't matter if I balance the carbons or the hydrogens first, but because this is a combustion reaction, I have to save oxygen for last. So I'm just going to start at the top with carbon. Because I've got more carbons on the reactant side than the product side, I need to work on the product side. And I need the coefficient 3 right there. That gives me 3 carbons. And I have these 6 oxygens. Remember, it's distribution, so it's multiplication. 6 oxygens plus 1 oxygen is 7 oxygens. Next, I'll balance the hydrogens, 8 versus 2. So I go up here, I need the coefficient 4. 4 times 2 gives me 8 hydrogens. There's 6 oxygens right here, plus another 4 oxygens right here. That's a total of 10. And then I ask myself, what is 10 divided by 2? It's 5. So that's the coefficient that I need right there. And again, because we've been nice and neat with our organized accounting table, we can easily scan left and right and see that it's balanced. Conceptually, here's what's going on. We have a single propane molecule, C3H8. It's reacting with 5 diatomic oxygen molecules, 1, 2, 3, 4, 5. It produces 3 carbon dioxide molecules, 1, 2, 3. You can spot the central carbon in there. It also produces 4 water molecules, 1, 2, 3, 4. Also gives off light and heat energy. All right, thanks a lot, guys. Have a great day.